We're waiting for people to join. Looks like no one is still here, so we'll start in 2-3 minutes. Let's wait for a couple more minutes and then we'll get started. Hope you can hear me and see my screen. If not, please drop a message on chat. Great, thank you. Okay, let's get started. So, welcome to the week 2 live session for the GPU architectures and programming course. Okay, yeah, let's get started and people can keep joining. So, I hope all of you attended last week's session, but for those of you who have probably missed it and are attending for the first time, I'll quickly go through this so that you get an idea of what to expect. So there would be one 2 hour live session conducted every week at the same time, which is Monday 7 to 9 p.m. And the main point of these live sessions is to focus on problem solving. to apply the concepts that you have learned in the course to solve certain sample problems. And this will help you in solving your assignments too. We will not discuss the exact same questions, but they will be similar. And once your assignments are submitted, if, for instance, the solution key comes out and you still don't understand something, we can go ahead and discuss that. But while the assignment is still in progress, we won't be discussing an exact question that is part of the assignment. Apart from that, you can also bring up doubts from that week's course content. So, what I mean here is, for instance, today we are doing the week 2 live session. So, we will go through all of any of week 2 doubts that you have. And sometimes I might say, depending on the time that I have, I might say I'll address it next week. But broadly, we will try to follow this, that every week's live session will cater to that week's course content. That way, it gives both you guys and me a good structure. We know what to prepare and come for, right? Yeah. And please keep it interactive, post questions on the chat box, and even these assignment problems that we'll solve, whether they are numericals or straightforward MCQs, please answer. It doesn't matter if you're right or wrong. And if you think something else is the right option also and you don't understand, please ask. I may or may not be able to clarify it in the same session, but I'll definitely address your doubt. And it's important that you get it clarified so that that concept is clear for you. That's the whole point of the live session. And post the session, you will get access to the slides and the recording. So don't worry in case you have network issues or you drop off or something like that. So that's about it. So since we have 2 hours, here's how we are structuring the sessions. So first 20 minutes will be a quick recap of a few topics. So last time I think I went over a bunch of topics and people even said I didn't understand something. So based on that, I will go deep into certain concepts that people have not understood, and I will kind of skim through certain other topics. But the point of doing this is for you guys to say, okay, I don't understand this particular topic or this particular subtopic. Can you please explain it in more detail in the next session? I can definitely do that. That's exactly the intent behind the live session. So feel free to ask. And after this, we will move on to the problem solving. So this is expected to be roughly 1 hour. So they are basically your previous year's assignment questions. And I'll be, like I said, I'll keep it interactive. You'll get time to solve the questions and you can post your responses on chat. And then the last 30 minutes, again, we'll keep aside for any doubts or any other questions. And we'll also go through the questions posted in the discussion forum. And since it's a 2 hour session, I will give a 5-minute break around the 8 o'clock mark so that you guys don't get too saturated by 1 hour. Feel free to take that break to do whatever you want to do. Come back around 8:05, right? Whatever time we break, 5 minutes from then, we'll be back. And if you want to do something different, for instance, if you say, I submitted assignment 1 this week and I got back the answers, but I'm still not clear. Can you discuss the entire assignment 1? That is something we can definitely do, right? So the structure is based on what I think would be useful to you guys. But since you are the ones actually benefiting from it, I want you guys to think about it and tell me also that this is helping us, this is not helping us. Can you do this, right? I'm very open to that and I'll try to accordingly structure the future sessions because we have 12 sessions in total and we are just at the second session. So feel free to do that at any point. I'll ask in the last 5 minutes also specifically on the structure of the live session. So hope the logistics part of it is clear to everyone. Does anyone have questions, especially people who joined for the first time today? Do you have an idea of what we'll be doing in these 2 hours, or are you still kind of confused? Okay, I'm assuming no one is confused. So, so to talk about what your recorded lectures covered for week 2, it was broadly an introduction to GPU architecture, right? So we started off with vector processors and then went into a little bit of SIMD and then GPUs. and broadly spoke about ideas such as data parallelism, SIMT. And then coming to GPUs itself, we looked at graphics pipeline, we looked at the first ever GPU in the world, and we looked a little bit at the Tesla architecture and maybe even Fermi, I think. And then we spoke briefly about the ISA, the memory hierarchy of the GPUs, and then we also touched upon various classes of GPUs, for instance, the mobile or embedded GPUs and the integrated GPUs. So we'll be focusing on these topics for today's problem solving session. Let's get started. So, a couple of things that people mentioned they were not clear about in the first week. So, I've kind of picked out examples so that this is clarified. So, pipelining, like I said last time, is a basic concept, right? So, it's important for you to get it right. Whether it's GPU architecture or even just plain computer architecture, pipelining is a concept that you'll find throughout. So I think two or three people told me that pipelining is not very clear. So I think I tried to explain with a rough example last time. But this time we'll go through a toy example and also come back to the 5-stage instruction pipeline. So let's start with this famous laundry example, right? So we have four people here indicated by A, B, C, D, which stands for Anne, Brian, Kathy, Dave. Each of them have one load of clothes. So this is a very relatable example, right? That's why we're starting with this. Unlike your instruction pipeline, where if you've never done Compark before, you might be kind of confused by what these stages themselves are. In contrast, this is very easy to relate to. So the three stages here are wash, dry, and fold. And the washer takes 30 minutes, the dryer takes 40 minutes, and the folder takes 20 minutes. These are our assumptions. So for one load of laundry, it takes 90 minutes. How is that 90 coming? You have 30 plus 40 plus 20. So this is your base case, what we start with, right? Without any pipelining, without any optimizations, just sequential execution. You have three stages: stage one, stage two, stage three, and the sum, the time it takes for one load. If you remember the concepts that we spoke about last time, this time that it takes for one load is actually called latency. So if you put your clothes in the washer, the time it comes out at the folder would be 90 minutes from the start time. So that's the basic idea. So now if you look at sequential laundry, here for instance, we said there are four people with one load of laundry each, right? That is your A, B, C, D. And now each of those, as we discussed in the previous slide, takes 90 minutes. So you have 90 minutes here, 90 minutes here, 90 minutes here, 90 minutes here. 90 minutes is 1.5 hours. So for four loads, it's 1.5 into 4, which is 6 hours, right? Again, there is no pipelining here. This is simply sequential laundry or sequential execution, right? This time axis might seem a bit complicated, but ignore that. It's simply 4 into 1.5 at this point, which is 6 hours. Now starts the idea of pipelining, right? So now the sequential, keep this number in mind, the sequential took 6 hours for 4 loads. Now here, observe carefully what's the difference, right? So A is doing that first load of laundry, and the washer has finished and the dryer is now executing. So what at this point, the washer is free or the washer is idle, right? But in case of sequential execution, it remains idle till this whole load of laundry gets done and the second person comes in to put their load. But that's kind of a waste of the washer, right? You, if let's say you own this laundromat, what would you always like? That your hardware is utilized fully because you're getting your full value for money, right? So now think about this. So why can't person B start their load of laundry while person A's laundry is in the second stage? They can, right? Because the washer is free. So that is what happens here. And similarly, while person A's laundry is in the folding stage, the dryer is free because the drying stage is finished. So this workload or person B can use the dryer while workload A is in the folding stage. So it's kind of an offset by one, right? Shift the entire thing by one. So that what is our goal? One goal is that the hardware that we have, in this case, which is the washer, the dryer, and the folder, are always in use. The are used to the best extent possible. Let me not say always in use, because that might not be the case in some pipelines, but to the best extent possible, we want to use them. The second thing we want to do is also reduce the overall time. So now if you look here and you do this math, I'm going to leave this math to you, but it's very easy. So I'm sure you can do it, right? It comes out for the same four loads, it comes out to 3.5 hours instead of 6, right? So that's a benefit that you get. But again, like I was highlighting last time, the difference between latency and throughput, right? Think about how much time one individual laundry load is taking. It is still taking the same 1.5 hours or 90 minutes. But what is the difference now? So the latency doesn't change, the throughput changes. And that's where pipelining is meant to help, right? Because you're using your hardware much more efficiently. In the instruction execution cycle, you have one instruction finishing execution in every cycle. We'll look at that in a bit, but hope you get the idea. So this example, go if it's still a bit confusing, go through this example offline. I'm sure you'll understand it. So this is the simplest way I can think of to explain pipelining, and I've given the link to the original set of slides from where this example is borrowed. But yeah, so that's the example for pipelining. And like I said, the motivation is you want higher throughput. So you want more work completed in one cycle. So when an instruction is using some resources, there are other resources that are idle, right? So you can use those idle resources to process other instructions. That's the whole idea. And you have different examples here based on the decode, fetch, and things like that. So, right. And I think the original week one slides mentioned the 5 stages, but it didn't have this pipeline diagram, right? So, what I would recommend for you, if you're still a little confused about the pipelining concept, is to draw out such a diagram, right? So, the x axis would be your clock. Clock numbers, or roughly you can even think of it as time, and you can think of all these different instructions and figure out which stage they are in which clock number. So for instance, I starts from the so to give a quick recap, there's fetch, decode, execute, memory, write back. Those are the equivalents of your washer, dryer, folder here, right? So it's a 5 stage pipeline. So instruction I would go through all of these five. Instruction I plus 1, at the very next clock cycle, at clock cycle 2 itself, it starts in the fetch stage and goes on. And similarly, one more offset for I plus 2, one more for I plus 3, and one more for I plus 4. And if you notice now, every one of these stages is being continuously used. So for instance, a write back is used in clock 5, in clock 6, in clock 7, in clock 8, in clock 9, right? So draw out this diagram for a non-pipelined execution and for a pipelined execution. You'll automatically understand the points both about throughput and about hardware utilization. Also write down the throughput for this, write down the latency for this, and write it down for the non-pipelined one as well. So that, I think, should clarify most doubts. Does anyone still have a doubt on pipelining? Okay, I'm guessing not. So the other question I think I got was what? Great, it's clear. Good to know that. Someone is joining. One second. Yeah. So the other question I got was, what are pipeline hazards? So now that you've seen this, right? This is an ideal pipeline. Like we want things to execute this way. But that might not actually be possible in reality because of some reasons. So, what could those reasons be? Broadly, they would be classified into three types: structural hazards, data hazards, and control hazards. So, structural hazards come from a resource conflict, that is, two things using the same unit. So, for instance, if uh, let's say, I think the example that was given in your lecture was the memory and the fetch, right? Both of them use the memory, and the hardware might not be capable of supporting both of them. Even though you draw out this pipeline diagram like this, if two stages in this use the same hardware, then and the hardware is not supporting that kind of parallel access, then you might have structural hazards. The other kind of thing you could have is data hazard, where you have some instruction that depends on the result of a previous instruction. And in sequential execution, this is fine because till instruction I has fully finished executing, you wouldn't go on to execute instruction I plus 1. But now in pipelining, while instruction I is executing, you're parallelly picking up I plus 1. So suppose I plus 1 is using some value that I is writing to, then that might be a problem because the write might not have happened when I plus 1 comes to the execute stage. I think I have an example for this, so let's wait. So broadly, data hazard means that there is some data dependency between instructions, and because of pipelining, this might be a problem. So pipelining is an optimization by which you improve throughput, right? But you don't want to change the program behavior. That's a really bad thing to do. For instance, let's say you compiled a program. Now you all of you might have used some compiler flags. Let's say you use C, you might have said -o1, -o2, something like that. So you know that the compiler is going to make some optimizations behind the scenes, which you are unaware of. But if the compiler, under the guise of making those optimizations, changed your program output itself, you as a user would be very, very unhappy because a compiler is not supposed to do that, right? It's just supposed to optimize your execution, not change program behavior. So while doing something like pipelining, it is it is the responsibility of uh, the pipelining design to take care that there is no change in program behavior. So data hazards are one of those. And then control hazards, you could have something like a branch instruction coming in. And then again, because now you're doing pipelining, you might have some issues because of that. One issue, for instance, which is not really a hazard, it might be a stall where the pipeline just waits. Because let's say you have a branch, right? So I say if condition, go to this part, else go to some other part. Now, while you're doing pipelining, you might fetch all the parts immediately following the if, right? Following your sequence of instructions. But let's say the control goes to the else part of it. So then you all the data that you've fetched and you've kind of gotten ready, you might even have executed some of the instructions. All of that needs to be just thrown away because you're taking a different branch now. So till and now you have the additional wait time of that branch instruction being fetched, decoded, executed. Till then, the pipeline will just wait. So that's called a stall, right? So when things like branching are there, there are a lot of those issues that come in. That's why there are branch prediction techniques that are used, and we studied some of them, right? We looked at, I think, a simple 1 bit and then a 2 bit branch predictor to address issues like this. But broadly, this is what a hazard means. And ultimately, if you have a stall in the pipeline where nothing is happening, then it would reduce the performance. That's the overall idea. So I hope this was clear. And let's look at the specific example. I've just put in one for data hazard. I think you guys can go look up the others. And if you still have questions about any particular thing, then come back and ask me. We can take it up again. So here we have two instructions. The first instruction takes as source, let's say these are, takes as source 1 and 3 and then populates the result into 2. And the second instruction takes as its source 2 and 5 and then populates the result into 12. So now there is a data hazard here, and the type of data hazard, so there are various types of data hazards. So read after write is the type of data hazard here. So you should be reading this value 2 only after it is written, right? If not, you will have a change in program behavior, because now what you'll do is you're going to read the previous value of 2 before this sub instruction modified it. And that is definitely going to change your program behavior. So exactly how that would happen is, if the sub is in the fetch stage in I plus 1th clock cycle, then this 2 would be updated in the I plus 5th cycle. Just think of the 5-stage pipeline, right? That's how this happens. And if the AND is in the execution stage in I plus 4th cycle, which is before this, right? So the updated value is not yet ready. So that is a problem. So you if you don't realize that there is a problem and blindly execute the pipeline, you might get you end up with a data hazard, and you might end up with wrong values that modify the program behavior. So how do you address something like this? For curiosity's sake, there are things like forwarding done directly to the execution stage. But again, this needs suitable logic first to detect the hazard and then to forward to that unit, right? So there are a lot of things that happen behind the scenes with pipelining, and hazards need to be taken care of. That's the main idea. I think this is all I had on questions from last week's content. Hope that was helpful. People are still joining. Okay. So with that, we'll move to looking at a couple of questions from the discussion forum. So again, I think we solved a very similar question last week, but since this was explicitly asked, it also has an answer on the forum. But for people who haven't seen it, I think it will be useful to quickly discuss it, right? So here the question says a non-pipeline processor was redesigned. Okay, how do we prevent hazard problems? So we can't we basically detect them and do something to address them, right? So whether you can prevent a hazard is kind of questionable, because think about this example itself, right? You as a computer architect have no control over what will the program be like. So let's say the user has written some high level language code that translates to these particular assembly instructions. You have no control over that. So there is a hazard here, right? What can you do when you're implementing pipelining? You can detect that hazard and then address that hazard somehow, so that your pipelining does not change the expected behavior. So here one example where you're addressing that hazard is by forwarding the data directly to the execution unit. But there are other ways to do it too. And I don't think we'll touch upon many of them here, because again, this is just basic computer architecture overview. If you look at an advanced computer architecture course, maybe I think you'll find some more ways of addressing them. I think one thing we briefly spoke about in the first class was also register renaming, right? That is a method used to address hazards. And Tomasulo's algorithm, which again was mentioned in class but not discussed, is also a very popular and well-known algorithm that deals with things like this. So you can look that up. But I think that is too detailed and kind of outside the scope of this course. So I don't think it would be useful to discuss in detail here. But broadly, those are the things that you can do. Anything else? Okay, moving on. So, yeah. So the question says a non-pipeline processor was redesigned as a five-stage pipeline processor. The different stages have different latencies. The stage-wise latencies are 300, 500, 600, 800, and 100 picoseconds respectively. Each pipeline stage incurs an extra 50 picosecond latency on account of the registers between pipeline stages. So I think the question was to find the latency and the cycle time both in the pipelined and the non-pipelined case. And I think someone had a doubt about that. So I've just put in the solutions here and we'll look through them briefly. I think we did it in detail last class, so this shouldn't be too difficult. So for the non-pipelined case, the cycle time would basically be the time for the instruction to go through all the stages of that are there, right? So all five stages: fetch, decode, execute, memory, write back. So you sum up all of this, which comes to 800, 1400, 22, and 2300. So that is the cycle time. And the latency, which is the time it takes for one instruction to go through all of these stages, is the same as the cycle time in the non-pipeline case. So that also comes to 2300. Now, in the pipelined case, I think this is where the person who asked the question also had a confusion. So, how do we set this cycle time, right? I think that part is the crux of answering this question. So, I think it was discussed in class also that you pick the slowest one because you want your cycle time to kind of accommodate for the slowest stage. So, in this case, that is 800, and additionally, you have a register latency at the end of it, which is 50 picoseconds. So it becomes 850. So remember this in the when you set the cycle time, it would be bound by the slowest stage, right? That's always a limitation to pipelining. So visually, if you have to visualize this, see, for simplicity's sake, we've kind of drawn all of them as equal squares, right? But they're not equal. And if you draw out a pipeline diagram where one of them is maybe 10x of the other, here it's kind of comparable, 30, 40, 20. But let's say you take 30, 320, right? And try to draw that out. You'll immediately see how that slowest instruction kind of holds the pipeline back. But that's the key idea here. So that's how you get cycle time. And now once cycle time is set, you won't go and add up each of the individual stages like we did in the non-pipeline case. Why that is even some of these stages might be faster than 800, right? For instance, 300, all of these, in fact, because we picked the max, right? So all of these are faster, but in a way, it's now like changing the clock cycle, right? So till the clock transitions, none of them can move to the next stage. Think of it like that. It's like artificially synchronizing all of them. So for instance, if you're running a race and there is one fast person and then a person who runs kind of at a medium pace and another one at a slow pace, what you're essentially doing is asking everyone to run at the slowest possible pace. So they run together. So now if I ask you how much time does each one take, you're not going to do fast plus medium plus slow, right? Because you've asked all of them to now take the same time. So similarly here, you will be doing 850, which is the time per stage into 5. And that's how you get this answer. So I think that was the confusion. So hope this clarifies that. Okay, moving forward. Right. This is just a minor thing. I think I mentioned it last time also that there is a correction in the questions for week one. But I think still someone thought that that correction applies only to one question. So remember, many of your assignments have this format that the data is given as a common block for a bunch of questions. So when you read, when someone tells you that there is a typo in this question, unless they specifically mention otherwise, it means that you will use the new data that they are giving you for all the questions for that block. So there, I think the doubt on the discussion forum was that does it change only for that particular question or for all three? And the clarification is that it applies for all three. So you'll have to solve all three with the data that is given on the discussion forum. There is a thread for this. So in case someone is confused by the week one assignment solution, this is kind of the correction and what questions it applies to. Right. With that, I think we've come to an end. So, with this, I think I have covered everything in week one and questions, discussion forum, doubts, and things like that. And right, about last week's live session, I think there was one question which had a cash rate and a CPI calculation, right? And I think one of you got it right, and the official key that was given and that I presented in the video was wrong. So I actually checked after the session and there was a mistake. And so I've corrected it in the slides. Hope you guys have seen the slides. So whenever after a live session, right, if there is a confusion about a particular question, I definitely make sure to go back and check the answers. And when before I put up the slides, I'll make sure that I put the updated slide with the corrections. So please, if you're referring to any of the live session materials, please refer to the slides as well once. Even if you're referring to the video and I say there that I'll check on this and I'll clarify it, please go back to the slides and check if there's any correction. So that was the only correction from last time and that has been updated in the slides. So as far as I am concerned, week one, I think we've completed everything. So and I'll take a minute now to see if you guys have some doubts still with week one content. If so, post it on chat and we'll still handle it next time. It doesn't matter. Assignments, the lecture material itself, assignment solution, whatever it is. Are there any doubts? Are there any things that are not clear? I'll wait for a minute, think about it, and let me know. Okay, I'll take that to mean there are no doubts. So let's move on to week two, right? So let's start with this graphics pipeline. I don't know if the diagram is visible. I'll try zooming in a bit. So this is a typical graphics pipeline that you have, and I think we studied the a little bit about the individual stages as well. So there is an input assembler stage, and then a vertex shader, a geometry shader, a rasterizer, a pixel shader, and an output merger. So this is how typically a graphics pipeline looks like. And what do each of these stages do, right? So the input assembler collects the vertices and primitives. The vertex shader maps the position of these vertices onto the screen, and it changes their position, color, or orientation as needed. Then finally, the geometry shader operates on geometric primitives. So the abstraction changes from here to here, right? So both of them are shaders. The vertex shader, as the name says, operates on vertices, whereas the geometry shader operates on geometric primitives such as lines or triangles. So it's one abstraction higher. Each of these primitives are defined by multiple vertices, and then it manipulates these primitives as needed. So that's a typical graphics pipeline. Why this is relevant? So today in the modern day GPU world, you might not hear people talking a lot about the graphics pipeline, right? You'll more likely hear about things like deep learning applications and lot of ML and DL stuff, right? Which is weirdly enough, if you've been following the history of the GPU, not what originally the GPU was intended to accelerate, right? It was just a clever um, application that it was kind of extended towards, and then now that has become the dominant use case. But this graphics pipeline has been there for a long time, and I think you have some questions on this as well. So you might not be able to relate to it a lot. This might seem very theoretical to you, but I think for this course, if you're able to remember what each of these individual units do, that should be enough. That's typically what, looking at the previous year's assignments, that's what you're questioned on. So just understanding this should be enough. Moving on. So yeah, this is also another interesting thing. Um, so when we say GPUs, most people typically we imagine high-end graphics cards that are kind of plugged in through a PCIe Express, right? This slide is to kind of tell you that there is a lot of variety in the GPU space itself, right? So for instance, you have mobile GPUs. A lot of mobile phones these days have GPUs, and again, the idea is that they accelerate graphics as well as compute tasks. So all your gaming and very graphics intensive workloads, and if you have some compute task running, right? For instance, in the deep learning space, I'm sure all of you use some kind of a keyboard, and you see that the keyboard predicts what you're going to type, right? And in a lot of such applications, federated learning is used. It's a form of distributed training where, let's say, you type a sentence, and it tries to learn from what you type, right? So that might be some form of compute that runs on the GPU. So it's GPUs on the mobiles also are used for deep learning in some form or the other, not just graphics. And then apart from this, you might have also seen some embedded boards for it. The Jetson line, as was mentioned in class, right? The Jetson Nano, Jetson TX, NX, Xavier, and recently I think Orin. All of these are NVIDIA's embedded GPU boards. So they're very small and compact. So think of a Raspberry Pi. I'm sure all of you have seen that. These are slightly bigger than that, but they're still nowhere close to a proper desktop GPU. What's the other difference in terms of these? They are far more power efficient. For instance, your desktop slash server GPU might be consuming hundreds of watts of power, whereas these embedded GPUs, they take less than 20, 30, 50 watts, max of I think 50 watts, right? So they consume a lot less power, they're a lot smaller, and they might be slightly cheaper too. And what's the trade-off for all of that? The compute that you get is not so powerful, right? Just how your mobile phone CPU might not be as good as your laptop CPU. Similarly, these GPUs are also not as powerful as their server grade counterparts. But it's interesting to be aware of them and to actually go look up what they're being used for, right? And drive also, which was mentioned in class, which is the third point here. It's also one of the embedded line, and it's intended to go into the autonomous vehicle space. So these are all not just GPUs, but they are complete systems, right? So they have a CPU, they have a multi-core CPU, they have a GPU, they might have other accelerators that are intended for specific workloads, and they'll also have a lot of IO and things like that. So it's an entire board that you can use. So drive is also one of them, and I think a lot of hardware vendors who are trying to get autonomous navigation going in the next few years are actually working on drive. So look up these things just to broaden your own definition of what a GPU looks like, right? It's not just the server and the desktop range of GPUs. There are also these. And similarly, there are also integrated GPUs. So you might see that, for instance, sometimes, typically, I think very few people are familiar with the fact that there is something called an integrated GPU. For instance, if you're going to buy a laptop, you'd think of it as, do I want a laptop with a GPU or without a GPU? But in reality, most or all laptops have a GPU anyway. Even if you don't buy a laptop, you think you're buying a laptop without a GPU. What you're actually getting is a laptop without a discrete GPU, which is a card that you plug in through PCIe, right? There is something called an integrated GPU. So if you go look at a normal laptop which has no NVIDIA GPU, you'll still see an Intel, if you have an Intel CPU, that is, you'll still see an Intel integrated GPU listed, and that still accelerates a lot of your graphics workloads and things like that. It might not be as powerful as the discrete GPU, but it is still a GPU, right? This might be something you're not aware of. So next time, even now, right, if you have a laptop, go look it up, see what kind of GPU you have. And if you have a discrete GPU, check how many GPUs you have. Do you also have an integrated GPU? And what is the advantage of an integrated GPU? As this point says here, the memory is kind of shared between the CPU and the GPU, the DRAM basically. So if you've seen the RAM card that you plug into the slot, typically, when you talk about discrete GPUs, they come with their own memory. You might have heard GPU memory is 4 GB DDR5 or GPU memory is 2 GB DDR5. Now, what that means is that anytime you have to run a workload on the GPU, you will have to copy some amount of data from the CPU RAM, the main DRAM, which might be 16 GB or 32 GB in your laptop's case, to the GPU DRAM, right? And this is in case of a discrete GPU. Now, in case of an integrated GPU, there is only one physical DRAM, and this is shared between the CPU and the GPU. So, what is the advantage of doing this? Basically, that you don't have to copy this data. So, think of it, every time you're sending something for compute on the GPU, you also need to copy out that data, right? And that's some overhead and some penalty in terms of performance that you're paying. Whereas now you might have what's called a zero copy, where you don't actually have to do a transfer as such because it's the same physical memory, but you might still need to do some bookkeeping. For instance, you might need to do some pointer management or something like that, so that both of them can use it. And additionally, you have to manage the caching aspects of it, keep maintain coherence and things like that. But that's the main advantage of integrated GPUs. And the downside of it is that you have more contention or competition for the DRAM bandwidth, right? So for instance, if your bandwidth is 100 Gbps, now the CPU is also going to try to get some memory, and at the same time the GPU might also be trying to get memory. So in essence, there is competition for the same bandwidth in case of integrated GPUs. In case of discrete, this is not the case because GPU works with its own DRAM and CPU works with its own RAM. And whenever GPU needs something, there is a copy that's actually done. So if you have a file sitting on disk, there is one copy from disk to main memory, which is the CPU RAM, and then one more copy from the CPU RAM to the GPU RAM. So that's an overhead of the discrete GPU. This is just for curiosity's sake, but since we are studying GPU architecture, I thought it would be good for you guys to know the differences in various classes of GPUs. Okay, so I didn't want to go into too much recap this week. So I've kept a couple of topics for next week. Basically, the SIMD versus SIMT. Again, that's a fairly important topic, and I think it might have been confusing also. I don't know. So, was it confusing, or do you guys understand SIMD and SIMT very well? If so, I'll skip it. If not, this was what I'm planning to cover in next week: memory hierarchy and SIMD versus SIMT. And feel free to add any other topics from week 2 that are not clear. So I'm assuming all of you have gone through week two's lectures. Are there any topics that are not clear? Okay, don't know SIMT. Okay, let's cover it then. I think that's an important thing to understand in terms of GPUs and the overall evolution from vector processors to SIMD to SIMT. Any other topics that you guys would like to see covered from week 2? Something that you didn't understand or something that left you very confused. Was there something like that? I'll wait a few more seconds to see if anyone has any topics. If not, we'll move over. I think we have the problem solving coming up next. Cash miss penalty question. Okay, so this is from the week 1 assignment questions, right? Okay, got it. Yeah, I'll put in a slide on that next time. I fixed it in the original slides, but I think it'll be good to go over it also. Noted. I will put that in next time. Anything else? Okay, if not, let's move forward. Yeah, so I think most of the questions today, unlike last week, most of them don't involve solving numericals. So I'll wait for a shorter amount of time, maybe 30 seconds or 40 seconds, something like that, and let me know what the answer is. Take your time, think about it, and let me know. So the first question: von Neumann architecture is not suitable for realizing SIMD. True or false? Answers: true. Okay. Anyone else? I think there was something very similar in your assignment question, and by now I think you've gotten the solutions to that also. So it must be clear to most people. So what any does anyone think it's false, or does everyone agree with true? Okay, let's look at what the answer is. It is true, and I don't think you had an explanation of von Neumann architecture in the class. So I've just put in a diagram as well, right? So if you've not had a basic course on computer architecture, please go look up von Neumann and Harvard architectures, right? So there are two different types of architectures. So we'll talk about just von Neumann today. So in von Neumann, there is one memory unit for instruction and data. Basically, it stores both of them, right? That means that you have a bottleneck. You can't fetch both instruction and data at the same time because you have both of them are stored in the same place. That is one of the key characteristics of von Neumann. Now think of it, now that you kind of see the architecture, think of, is SIMD possible? So single instruction, multiple data. So first of all, with this kind of an architecture, is there a provision to fetch multiple data items at the same time? There isn't, right? So that itself kind of rules it out from realizing SIMD. So that's why when we spoke about SIMD, we started looking at very specialized architectures, right? Unlike the typical von Neumann or Harvard kind of architectures. But basically, that's why they're not suitable for SIMD. Is this clear? Okay, great. Let's see. I think now might be a good time for a break. I think we're almost at an hour. So we have, I think, 9 questions left. So we have enough time to go through them. So it's 7:57 by my clock. So we'll be back around 8:02. Feel free to use the break to get coffee or whatever you want, right? Just make sure that you kind of refresh and come back and don't feel too saturated. So see you guys in 5 minutes. Okay, let's continue. Question 2. Vector processors can handle data level parallelism. True or false? Anyone? Take your time, think about it. Okay, true. Anyone else? Okay, let's look at the answer. It is true, but let's first talk about data and task parallelism because I don't think we have so far. So these are essentially two different types of parallelism, right? And in the context of GPU, for the most part, you'll hear about data parallelism. But again, outside of that, also these terms will be used. So it's good to be aware of, especially the difference between data parallelism and task parallelism. So as the name says, in data parallelism, you distribute subsets of the data across multiple cores and you do the same operation on each one of them. So look at this figure. I think that should make it clear. So you have the data and you partition it among different tasks, each of which will run on different cores, right? But notice that all of them do the same thing. That's why all of them have the same label, right? And one second, right. But even though you're partitioning the data among multiple cores or multiple instances of the same task, all of them are doing the same thing. That is kind of characteristic of data parallelism. Whereas task parallelism is something very different. So let's say you have an array, right? Very simple example. You have an array and you're trying to calculate maybe sum of the array. And let's say you're trying to calculate product of the array and some three different unrelated things like that, right? Now, what you can do, so in the sum and product example, for instance, task one will be sum and task two will be product. And the entire data, the entire array is fed to both task one and task two. So here it's not the data that is partitioned, it's the tasks that are partitioned. And here you benefit because your application had two tasks that were kind of unrelated. And now you're running both of these tasks on different cores, right? So you're utilizing hardware in parallel and that will give you a benefit. So this is kind of what task parallelism is. And here the difference again is that each of these tasks are distinct or different. In our example, one of them was addition, the other was multiplication, could be something else, right? But that's how task parallelism works. And how do you decide which of these parallelisms can be used for your workload or for your example? You look at the use case, right? If the basically the problem dictates the type of parallelism. If your problem has something where it would benefit from task parallelism, then use that. If it has a structure where it would benefit from data parallelism, where essentially you're doing the same task across multiple subsets of data, then you would use task data parallelism, right? That's the idea. But in GPUs, most of the time it is data parallelism. And I think we looked at multiple architectures that kind of use this idea of data parallelism, and one of which, the first of which was vector processors, and then followed by SIMD, and then finally the GPUs. So coming back to the question now, vector processors can handle data parallelism, and they are one of the architectures that was designed to support data parallelism. So hope that is clear. Any doubts on this? Okay, if not, let's move on. Vector processors contain only vector registers, true or false? Okay, this question on the previous one. Why does vector processor not support task parallelism? So, these ideas of parallelism, right? They can be, you can you can execute them in different fashions. But here we are talking about, so for instance, right, we talk about uh, SIMD, and there are these vector extensions like AVX, MMX, and things like that. So your x86 processors or your typical Intel CPUs can also execute SIMD, right? But here it's kind of, what is that architecture designed to do? Vector processors are designed to work on data parallelism. So if you wanted to do task parallelism, is there a way to do task parallelism on vector processors? There might be, but it wouldn't be with hardware support. That's what hardware or ISA level of support, right? There are different ways of doing something. For instance, you might have, um, let's say your processor only supports integer operations, integer multiplications, integer additions, and things like that. Is there a way for you to still implement floating point operations? There might be, but it will be done in software. It won't be done using hardware units. And what what happens then is that you take a performance hit. Even though you might be getting the expected answer, in terms of performance, it is not efficient enough. And that's why, so here we are going one step further in designing an entire architecture to support a certain kind of uh, parallelism, for instance, data parallelism, right? And is it not possible to do task parallelism? I'm not very sure. It might be possible, but it wouldn't be as performant as this, because the entire stack here, starting from the architectures to the instruction set that you have, the instructions that you have, and then the programming interface that you have, all of this kind of caters to data parallelism. So that's why we say vector processors can do data parallelism. Nothing more than that. One more example for this, for instance, in the operating systems world, there is a page walk, right, that is done. So basically there is a virtual address that a program sees, and that needs to be translated to a physical address that is on the DRAM. So this is done by the hardware using what is called a page walker, right? But you could implement the same thing in software as well, and it would work. But the problem is, every time you try to read something, you have to take that penalty of doing this in software. Hardware is typically more faster than software, because it's like custom designing a piece of hardware to do something, rather than having generic hardware that can do everything but is not really tailored for something, right? GPUs are your case in point. GPUs are meant to accelerate certain kinds of workloads. Initially, that was graphics workloads, and now it is a lot of deep learning workloads, right? In fact, GPUs are also called accelerators for that specific reason. So it's kind of that way. Think of it that way, right? It's not that you can't do something on a particular architecture, but it might not be the most efficient or the most easiest or convenient way of doing it. Hope that helped. That was a little bit of a complex answer, but hope you still got the idea. Okay. Great. So I think we were answering this. I think some people said false. Does anyone else have answers? Okay. Let's look at that again. I think this was a straightforward recall question from what was taught in class. So vector processors don't consist of only vector registers. I think we were talking about this whole architecture, and in the I've pasted the slide from the class, so where we say that there are vector registers where each vector register is a fixed length bank holding a single vector, but additionally the original scalar registers are also present, right? So that means that vector processors don't only contain vector registers, they also contain the original set of scalar registers. Why this is an interesting question. I myself haven't thought about it. Does anyone have an answer as to why you'd need the original scalar registers? Think about it. Would it be enough if you had vector registers? If so, then why do we have scalar registers? I won't spend time answering that, but think about it and we can look at it some other time, maybe. Okay, another kind of recall question. Tesla GeForce 8800 has a total of 128 streaming processors organized in 8 SMs. True or false? Anyone? True. Okay. True. Okay. Anyone else? Okay, let's take a look. So it's actually false, and it's again very straightforward, right? It's because it is organized as 16 SMs. 128 SP is organized as 16 SMs, and this is straight from the class slide. So there's no question of why this is or something like that. It's just about whether you remember how many SMs there are in this particular GPU. So if you don't, that's perfectly fine. Just go look it up later and it should be fine. Okay, the next question. Cache memory and constant memory are unified for all streaming multiprocessors. True or false? Again, I think there was a confusion about this also on the discussion forum. So we'll talk about it. But take your time, think about this, and let's see what answers we get. True? Okay. Anyone else? Didn't understand the question. Okay. Right. So that I think there was a memory hierarchy of GPUs that was discussed in week 2, right? So there were different types of memory that we spoke about. Things like global memory and local memory and other things, right? Where each of those memories were accessible to a limited set of things. The limited set might be threads in the same SM, might be all SMs, might be something else, right? So here the question says cache memory and constant memory, two different types of memory. They are unified for all streaming multiprocessors, as in all of them can access it or it is visible to all SMs. So that's all streaming multiprocessor. So that's kind of the question. Again, I feel some of these terms themselves you might not have seen or heard from the week two's lecture. That's why I'm planning to go a little more into detail into the memory hierarchy next week, because I don't know if you even heard the term constant memory during the lecture itself. There were certain other types of memory like local memory mentioned, but probably not constant memory. So we'll look at this again in the next week. But this is a question for now. So if you know what these types of memory are, maybe make an attempt at answering it. So I think we had a couple of people who said true. Okay. Okay, let's look at the answer. This might be something that people are not very clear about. That's okay. Oops. Right. So it is, the answer says false. And this is the formal explanation that was given in the discussion forum. So I've put in the same thing here. So, what is cache memory? Every SM has its own cache memory, and there is all this intermediate data that is generated during computation, right? Not the inputs or the outputs, but think of it as you might have four steps in the computation process. So, in going from step one to step two, there might be some data that needs to be stored temporarily. So this is stored in the cache memory, and it's an advantage because it reduces the number of global memory accesses, which means that you don't have to go access the DRAM every time you want to get all this intermediate data, right? And that helps you improve the performance because this memory is present in every SM, right? Not uh, across all of them in the DRAM. So that's the cache memory. The constant memory is, in contrast, a special type of memory that is used to store constant values that are required by the GPU kernels. So this need not be local to an SM, right? So if you're going to execute one GPU kernel and there are some constants that this GPU kernel needs, then it makes sense to store it globally, right? So that all SMs can access it and share the same constant, right? So this type of memory is shared across all SMs. So constant memory is shared or unified for all SMs, but cache memory is a per SM entity. So coming back to the question, therefore the answer is false. But again, I think you need to look at this in context of the entire memory hierarchy, which we will do next week. So we'll talk about global memory, constant cache, and any other types of memory there are. And after that, all your memory hierarchy questions should become very easy and straightforward. But is this clear for now? Okay, I will wait for a few more seconds and then proceed to the next question. Okay, let's move ahead. Okay, so this is from the graphics pipeline. Dash maps the position of vertices onto the screen, altering their position, color, or orientation. You have vertex shader, pixel shader, geometry shader, none of the above. Answers? This should be straightforward. Okay, A vertex shader, anyone else? Anyone? Okay, I think we have consensus on A. So let's look at the answer. It is vertex shader. And I don't have much of an explanation for this because I think what was covered in the class is only what each of these does, and that's exactly what's asked, right? So it's straightforward in the sense. So moving on. Dash fills the interior of primitives, including interpolating per fragment parameters, texturing, and coloring. Again, vertex shader, pixel shader, geometry shader, none of the above. Okay, B pixel shader, B pixel shader, anyone else? Okay, let's look at the answer. It is pixel shader. I think everybody got it right. Yeah, everyone got it right. Let's move on. Okay. Dash operates on lines and triangles defined by multiple vertices, changing or generating additional primitives in graphics. Same set of options. So that really reduces your search space, right? Answers? Okay. C. C. Any other answers? Okay, let's take a look. It is C geometry shader, and again, I think everyone got it right. Okay, let's move on. Dash is the world's first GPU, GeForce 100, 256, 8800, 80. Okay, C 8800. Anyone else? Okay, B GeForce 256. Take us for A or D. Okay. B. Anyone else? Okay, let's check what the answer is. It is GeForce 256. Again, I have no other explanations. It is the first. I think it was mentioned and it was probably somewhere in the late 90s, right? 98 or 99. That was the world's first GPU. And anyone has an idea on what's the latest, maybe NVIDIA GPU? If you guys follow the all the GPU news and the specs and performance reviews that you read about, what's the latest you've heard of? It need not be the latest as of today, but what's the latest you've heard of? Okay, Titan, I see. Maybe even the Hopper architecture and maybe RTX series, I see. Right. I think 3060s and 3060s are probably the newest, or maybe there's a 3050 that I don't know of. So there was 3090, 80, 70, and then 60. Nice. So I guess you guys follow the GPU news. That's good. Okay, moving on. Tesla architecture targets dash A. Increased latency for high precision math operations. Execute vertex and pixel fragment shader programs on the same unified processor. Decrease latency for low precision texture filtering, depth testing and stencil testing, color blending operations, etc. B. Okay. Anyone else? Again, I think most of this session is simply a lot of recall questions, right? So if you don't remember, that's fine. You can go look it up. Okay, B. Anyone else? Okay, let's look at the answer. It is B. Execute vertex and pixel fragment shader programs on the same unified processor. So, for some context on why Tesla wanted to do that, is you have two of these vertex processors, you have two of these entities, right? Vertex processors and pixel fragment processors, and both of them are designed with slightly different goals in mind. And if you have these implemented in hardware as fixed function blocks, then it's kind of difficult to load balance depending on the application. So the main objective is that they wanted to have these on the same unified processor. And why do that? Like I said, one thing is load balancing, right? If you have varying vertex and pixel processing workloads, if you have these as fixed function blocks in hardware, then it gets a lot more rigid to do any kind of load balancing. But if it's the same unified processor that's doing both, then you can vary the number of threads you want for each task and things like that, right? So that was the main goal, and that's why the answer is option B. Okay, I think we have a couple of numerical questions before we wrap up. So I'll give you more time for these. So a GPU having clock frequency at 3 gigahertz and 32 SIMD processors each, containing 32 single precision floating point units. What is the peak single precision floating point throughput for this GPU in terms of gigaflops per second, assuming that all memory latencies can be hidden? Assume that the concerned GPU does not support fused multiply and add. And you have your options as 768, 1024, 3072, none of the above. So I'll give you maybe 3 minutes for this question. Take your time and solve it. Okay, we already have an answer as C, but I'll give you time for people who want to calculate. Anyone else? I'll wait a minute more. So think of it, right? You want the throughput in gigaflops per second, which is broadly operations per second, right? The giga is just 10 power 9. Ignore that. Think about calculating number of operations, floating point operations per second, more specifically. How do you do that? You're given the hardware specifications, the clock frequency, and how many processors and how many single precision floating point units are given. Start with, if you had one single precision floating point unit and one SIMD processor, what would the throughput be? And then if you instead have now 32 and 32, what would it be? I'll wait for a few more seconds maybe, and then we'll look at the solution. Okay. The answer is 3072, but let's think about how we get there, right? So first we are given 3 gigahertz as a frequency. Broadly, you can think of that as 3 cycles per second. And if you think of one instruction per cycle, that translates to 3 per uh, second, right? And then this is again, like I said, with one single precision floating point unit. Now, if you have 32 of these, it would be 3 into 32. But you not only have 32 of these, but you have 32 SIMD processors, each containing 32. So it would be 32 into 32 into 3, which comes out to be 3072. So the math is quite simple, but I think what is a little bit tricky is going from the frequency to the number of operations per second. And this flops metric, if you're hearing this for the first time, it maybe go look it up, because typically, right, how do you compare multiple uh, pieces of hardware? For instance, GPUs. Let's say you're comparing an RTX 3060 and an RTX 3050, right? Now the frequency would could have changed. The architecture itself would have changed. So, what is a metric that you can use that is kind of agnostic to both of these, or that helps you compare across both of these? For instance, I can't blindly say that maybe the 3050 has a 3 gigahertz GPU, whereas the 3060 has a 2 gigahertz GPU. Therefore, the 3050 is faster. Might not be the case depending on other aspects of the architecture, right? So, a good way that many people compare GPUs is using this metric called G flops per second, or that basically stands for the throughput. And it can be single precision floating point operations, as in this example. It can also be full precision or double precision floating point ops, which is more typically used, right? When people say flops, it usually refers to the full double precision, not single precision. That's why it's specifically asked about single precision here. People could also talk about integer operations. These days, that's also becoming a valid metric. And there you'll hear terms like GOPS or TOPS, right? Without the FL, because that stands for floating point. So if it's integer operations, you'll be hearing terms like GOPS or TOPS, tera operations per second, or giga operations per second. So this is a useful metric to remember. But I think solution wise, it is straightforward. Any questions on this? We have one last question and then we are done. Okay, if not, yeah. So the last question is on Amdahl's law. Again, I don't think Amdahl's law itself was covered during the lecture, which is why the explanation is also given here, right? So Amdahl's law is used to find the maximum expected improvement to an overall system when only part of the system is improved. It is often used in parallel computing to predict the theoretical maximum speedup. Amdahl's law for overall speedup is given by speedup equal to old execution time by new execution time, and then there is a simplification of the formula, 1 by 1 minus fraction. So you can read that formula, right? So this talks about how do you compute speedup with Amdahl's law. And now we have a question which asks you to do that. So 70% of a program's execution time occurs inside a loop that can be executed in parallel. The maximum speed up we should expect from a parallel version of the program executing on 16 CPUs will be dash. So maybe make note of this information, and if you want, I'll go back to the previous slide and also show you the speed up slide again. I'll pause here for maybe 10-20 seconds while you make note of it, and then also go back to the previous slide. Okay, hope everyone got this. So I'll pause here as well for people who want the formula. and I'll give you maybe 2 minutes to solve this. Okay, 2.909. Okay, that is option C. Anyone else? I'll wait for 30 more seconds. Anyone else with a different answer? Okay, I think we can take a look at the answer. It is 2.909. So first of all, let's get the direct kind of substitution out of the way, right? So going by this formula, so here in the question, we said that 70% is parallelized using 16 CPUs and the 30% is as is. So this formula will now become 1 by 1 minus the enhanced was zero point 0.7, right? 70%. So 1 by 1 minus zero point 0.7. So 1 by zero point 0.3 plus uh, zero point 0.7 divided by 16, right? And if you do that, that would come out to be 2.909. You can try it out. That's the simple substitution part of it. But think about Amdahl's law is again one of those very important iconic concepts. So we'll spend a few minutes talking about it, right? Think about this now. You're parallelizing 70% of the program, which is like a clearly a majority, right? And you're parallelizing it by adding 16 CPUs. So don't you think the speed up or the reduction in time that you should get should be somewhere around 16, maybe at least 5 or 6, given that 70% is happening in parallel. But here you see that number is, maybe we can approximate this to 3, but you're getting a speed up of 3, meaning that previously if your program took 30 seconds to execute, now it would take 10 seconds, but you're adding 16 CPUs to do that. So is that really very efficient, and why does that happen, right? That's what Amdahl's law tells us. So the Amdahl's law is also known as strong scaling. So what is Amdahl's law about? So here we think of it as the total problem size is fixed. In our previous example, we said there is this program which needs to execute. Maybe let's think of it as a matrix multiplication of 1000 cross 1000, right? Now this problem size, that 1000 cross 1000, is fixed. So what does Amdahl's law say? The speed up is limited by the sequential bottleneck. So on the right hand of the image, you see this example, right? So there are two parts of the process. The one which is red in color, that's A, and one more that's blue in color that's much lesser. And now we are trying two different things here. Make B 5x faster. So you're trying to cut back on um, B, you're somehow parallelizing it, and B becomes this much. Now look at the overall execution time. And in contrast, you make A 2x faster, which is this portion, and now look at the overall execution time, right? So that's kind of what Amdahl's law tells you. Given that you enhance or you parallelize a certain part of the program, what does the overall time look like? What does the overall speed up look like? And you'll start to see this sequential bottleneck coming in a lot. So coming to the below example, there is this is kind of a half and half, right? Half is parallelizable, the other half is not parallelizable. Now you start to see that no matter how well I parallelize this half, the dominant part still remains. This part of half still remains. I've optimized this portion by 10x now, but because this portion is still there, it becomes a bottleneck. So the speed up I can get, even if I add 1000 processors here to parallelize this part, this will remain exactly as it is, and therefore my speed up gets limited. So if you look at the speed up curves, which are on the left, you see that they kind of saturate. Very soon they start to saturate. And depending on the parallelizable portion, you see how the curves change, right? The topmost, for instance, is 95% is parallelizable, but you see that even there, the speed up remains around 20. So 99% of your program is parallelizable, 99 or maybe that's 95. I don't have a second monitor today, so it's a bit of a struggle for me to read. But I think that's 95. So even then, the speed up remains at 20, right? Whereas if it's 50% parallelizable, you see that the speed up never goes beyond 2. So the x-axis is the number of processors. No matter how many processors you add, you can never speed up your program beyond 2, right? So the sequential part is the bottleneck. That's what Amdahl's law tells you. And more commonly, Amdahl's law is known as the law of diminishing returns. Basically, you're adding more hardware, but the returns you're getting for adding that hardware is lesser. It diminishes, right? That's Amdahl's law. Now, there is a counterpart to Amdahl's law, which is called Gustafson's law or also weak scaling. So, Amdahl's law is called strong scaling. So, what Gustafson's law says is that the problem size increases with the number of processors. So, here we said that the problem size is fixed and we kept on adding processors. We said we are doing 1000 cross 1000 matrix multiplication and I'm adding more processors. Instead, now I'm going to increase this 1000 cross 1000 to 10,000 cross 10,000, and I'm also going to add more number of processors. Now the assumption is only the parallelizable fraction of the input work increases with the number of processors. The serial part, which is like an overhead, remains the same. So you can see that the parallelizable work has now increased because the problem size has increased. But I also add as a counterpart, when the work increases, I increase the number of processors. So now the total time remains the same because the serial part has not changed. The parallel part that grew because of the problem size, I have parallelized by adding more processors. So the total runtime remains the same. So now if you look at the speed up curves, you see that you get something similar to linear scaling, right? Which is what you kind of want to see. If you're adding more number of processors, you expect to see a consequent speed up, corresponding speed up, right? So weak scaling is more easily realizable than strong scaling. Very few systems can strongly scale because you see that the sequential part of the program becomes very quickly, it becomes a bottleneck. So instead, what most contemporary systems do, They increase the problem size along with the number of processors, and they achieve weak scaling. So this is something just for you to keep in mind and be aware of, although it's not strictly part of the course. But since there was a question on Amdahl's law, it's good to know about Gustafson's law as well. So I think that's all I had, and we have 5 minutes left. So I'll take any other questions that you guys might have. Any questions? Was the last part clear? Also, any feedback since we're at the last 5 minutes? Any feedback on the structure of the session itself? Would you like to see more of something? Feel free to post whatever feedback you have on chat. If you don't have anything, that's all I will be talking for today. So I'll wait around for another 2-3 minutes to see if any of you have questions or comments or suggestions. But if you don't have anything, feel free to drop off. Thank you so much for joining, and I hope to see you next Monday as well. And hope this is useful to you guys. Two lectures per week, I think, will be difficult for people to attend, right? Because you guys have your own coursework and assignments and a lot of things like that. So, up until last semester, I think yeah, thank you so much. Thank you for joining. Up until last semester, I think it was 1 hour per week. Now they've made it 2 hours per week. But yeah, thank you. I'm still a little concerned that 2 hours itself might be a lot for people to join and listen. And if you see from last week to this week, from 20, I think we've gone down to 5 or 6 people, right? And 2 hours might be very difficult. So two such sessions, I don't know how many people will attend. So for now, we'll just have one session per week. Ah, great to hear that. Thank you so much. And very nice to see you guys taking an advanced course like this. Usually, systems courses, I think very few people are comfortable picking it up because it is difficult, right? It's not like a basic beginner level course, but it's very nice that uh, you guys have taken it up. Guidance on any particular thing? I didn't understand that very well. Guidance on some particular topic, some particular area. Okay, how do I use this in cybersecurity? That's going to be a link that's kind of hard to make. So GPU security itself these days has been increasingly prominent. Like I was talking about this keyboard training example, right, where your data is used to train something. Lot of such applications happen on the GPU. So there has been concern on security in the GPU. In the CPU side, and I think for a while there has been research. For instance, Intel has something called SGX or Secure Enclave. So similar such paradigms have been coming up for the GPUs as well, but that's not really cyber security. It's more generally in the area of security. But how you can use this course knowledge in probably cyber security is you have a very good understanding of the hardware, right? The GPU, and with these architecture basics, more generally the entire hardware. So maybe some hardware aware methods that you can propose to either detect or prevent or address security attacks that would be easier for you because you also have this additional knowledge of hardware and the appreciation of how things are designed at an architecture level. That's overall what I have to say. But cybersecurity is definitely outside my area of research, so take it with a pinch of salt. Okay, so I think we're at the end of the hour. So thanks everyone. Thank you so much for joining. Hope it was worth your time and see you again next week. Thanks.